We often take it for granted, but electricity is the lifeblood of our societies and economies. Our factories are powered by it, and it lights our cities. Coal has remained the dominant source of electricity generation through most of the last century, and it was still generating 37% of the world's electricity in 2019. Now we know that this dominance and use of other fossil fuels came at a price, sending our climate on a warming cycle with uncountable environmental and social consequences. This strangely beautiful construction behind me is the base of a cooling tower for a coal-fired power station at West Burton in North Nottinghamshire in the UK. This is all about to be decommissioned in a couple of months, and this whole area will start a new life, moving from fossil to fusion. The UK government has set itself the target of building the world's first nuclear fusion power plant here by 2040. Saran Postans is part of the UK Atomic Energy Authority team setting up the project. And what are some of those things that you need that this old coal-fired plant gives you?
So actually what's here will be decommissioned and taken down to ground level, so we won't use what's here currently except the connections to the national grid. And also we're right next to the River Trent here, so we'll definitely use the river as a cooling source for the plant. So actually what we need is the land. And this is a big site, it's 330 hectares in total. So we'll be using that land to its sort of fullest extent, not just for the step plant, but also looking at opportunities to bring adjacent industries and other things here as well. So it becomes a second kind of centre of excellence for fusion in the UK.
So we've seen a few breakthroughs recently, like the ignition in the United States recently, and Culham a year or so ago, sustaining a plasma for 5 seconds. Are you really confident that you can have a working prototype providing energy to the grid by 2040?
Yeah, so there's a joke, right, that fusion's always 20 years away. And absolutely, there are lots of challenges. There have been lots of challenges about why fusion hasn't come to the grid before now. But we really feel like there's lots and lots of breakthroughs. So we're really confident that we're kind of getting to the sort of scientific challenges and overcoming those. And then really it's about engineering and how do you bring all of the different components you need to have together in an integrated power plant, and that's what STEP's aiming to do.
STEP stands for Spherical Tokamak for energy production, and a tokamak is a type of reactor where fusion takes place. Nuclear fusion is the process that takes place in the heart of stars like our Sun, and recreating it here on Earth could create an unlimited, clean energy source. At its simplest, the Sun is a huge glowing sphere of hydrogen and helium. Its extreme temperatures and gravity strip hydrogen nuclei of their electrons, leaving the protons and electrons moving free from each other in what is known as a plasma. Because protons are all positively charged, they normally repel each other. But the Sun's extreme temperatures and huge gravitational force overcome this repulsion, forcing the hydrogen protons together, eventually fusing them into helium atoms. The new helium atom is slightly less massive than the ones that created it, with the missing mass released as energy. Because plasmas are a mass of charged particles, they can be influenced by magnetic fields. And that happens inside a containment vessel known as a tokamak, which is one of a number of ways in which scientists are trying to achieve fusion here on Earth. Previously on Razor, we visited ITER, the world's largest fusion experiment, which is building a tokamak reactor in the south of France. And JET, the Joint European Torus, is already up and running at the UK Atomic Energy Authority in Culham. These tokamaks use a donut-shaped reactor, but for the planned prototype power station, a spherical tokamak is being developed. Dr. Fulvio Militello, a fusion scientist with 20 years' experience, is currently the Director of Tokamak Science at the MAST upgrade experiment, which is testing the Spherical Tokamak design. It doesn't look like a sphere to me. It looks like a cylinder.
It is a cylinder that contains a sphere.
Ah, a sphere of plasma.
Yes,
Ah,
correct.
I see.
Correct.
Right.
The
okay.
sphere is around here. Your apple without the core is around here.
Oh, I see. So if we imagine it going like up there,
Yes,
then it's a
around.
sphere of plasma.
Yes,
Ah, right.
yes. It's a cylinder containing a sphere.
A cylinder containing a sphere.
Yes.
Tell me, what does MAST stand for?
MAST stands for Mega Ampere Spherical Tokamak. Mega ampere fundamentally tells us how much current is flowing inside the device, and spherical tokamak gives us our geometry. So these cored apples fundamentally represent a slightly different approach to fusion energy.
So we've had colleagues here before looking at the toroidal tokamak, the donut. What's the difference between that and your spherical tokamak?
So the difference between the experiment that we have at JET and the experiment that we have here at MAST Upgrade is fundamentally the shape and the size. And so the spherical design allows us to use less space. They give us a more compact device that can use more efficiently the magnetic fields that we're using to confine the plasma, to keep it in place. It is a way of reducing the cost of a future power plant, and that's essential, because otherwise the cost of electricity will be too high and it will not be there will not be competition with other forms of energy.
I'm confused. We haven't yet cracked fusion. We haven't got more energy out than we put in. Why are we experimenting with the shape?
We have fusion every day in our devices, but as you correctly said, we have not yet managed to amplify the amount of energy that we put in the device. A future power plant is going to be fundamentally an energy amplificator. You put a lot of energy in, you get much more energy out. We haven't done that yet, but we are on track to do this. The experiments that we've done at JET years ago have already shown that we can get almost to break even, which basically means as much energy in as we get out. And we think that by changing the elements that we're using in our machines in terms of plasma and changing the structure of the device itself, its size, we can reliably go to much higher energy amplification. But why is it useful to have the experiments that we are doing here? It's because we are building the physics knowledge that is required for future power plants. And we are also testing our tools. We are teaching our people how to operate devices, and we are creating also numerical codes that can allow us to understand how the physics of the plasma inside the device will behave in a future power plant. And we're testing this. And everything that we're getting from our smaller device, not yet power plant size, is indicating that we can get to the point in which fusion will become a reality.
So we just heard a countdown. We're about to fire a pulse.
Yes?
So we're actually going to see a plasma be created.
Yes.
Okay.
But it might take a little bit of time.
Yeah, no, well, let's just wait for that. Let's wait for that to happen. How much time do you think?
I will need to ask.
Yeah.
I think it could be a couple of minutes though.
Okay, that's all right. It's very exciting. So Fulvio's just gone off to find out.
Less than 60 seconds.
Less than 60 seconds.
Yeah, there will be a flash of light in the air.
In that monitor.
And then all the data will start appearing in the following minutes.
This is very exciting.
It's not going to be super exciting, no.
For me, it's exciting.
Okay.
You're used to it.
Yeah.
So that's the main screen we're going to be watching over there, Paul.
The plasma pulses here in MAST are relatively short. We don't need more than a couple of seconds. So you really have people gathering in front of the screen, looking at the plasma as it goes. Yeah. Here it goes. Yeah. You see the flash over there?
Wow.
It has happened. And now all the data are transmitted to our computers. The scientists are starting to analyze them. Some will arrive fast, some will arrive a little bit slower, and we will go for the next pulse.
So that tiny amount of time is giving you a multitude of information.
Absolutely. We have tens of diagnostics around the device that are looking at many different aspects of how the plasma behaves. Of course, visual cameras are part of the diagnostics that we're using, but there is much more than that. We have very sophisticated technologies that are used to analyze what is happening in a plasma. at the moment, we are trying to tackle two major problems that fusion has. One is to keep the plasma hot. The other one is to make sure that this stellar energy is not negatively affecting the internal surfaces of the machine. So these two things are both crucial for fusion, and they have to coexist. We have to make sure that both of them are working in the right way. It's a little bit like trying to keep your coffee hot in your mug and avoiding burning your hand. So what we are trying to do now in this set of experiments in Must Upgrade is to try to combine these two needs of maintaining the plasma hot and avoiding damages to the surface of the device at the same time.
So the trick is to keep the plasma as hot as you need for as long as you need, right?
Yes.
For indefinitely?
Not necessarily. So there are different designs in our community. There are ideas of having a pulsed power plant, which has plasma pulses of the order of a couple of hours. And there are other designs that are assuming much longer pulses that can be potentially of the order of many, many hours, if not days, if not weeks.
So you're not just working on the problem of fusion here, you're working on also at the same time how to take it to build a working power plant, aren't you?
Absolutely. Especially here at UKAEA, moving towards a power plant is a very strong focus of our research. After all, we are in the business of applied physics. We really want to deliver energy for the future generations. And we really think that we can do that if you want a noble cause to work on fusion. And it's actually extremely exciting also for a physicist. There is a very big intellectual challenge, and at the same time you get the reward of doing something that is good for all humanity.
While Dr. Militello and his team work on the plasma physics, the engineering challenge of building and running a fusion reactor is also being tackled. Professor Robert Buckingham is Director of RACE.
RACE stands for Remote Applications in Challenging Environments.
Remote Applications in Challenging Environments. That sounds a bit James Bond to me.
I think Tony Stark more than James Bond.
Why?
Yeah.
Why do you think that?
Well, you know, a Tony Stark fusion reactor on his chest, loves robots. We do a load of stuff on both of those things. So yeah, Tony Stark more than James Bond. He's a bit passé, yeah?
In what way, we think of nuclear fusion as completely benign. In what way is it a challenging environment?
We're trying to create a star on Earth. And when you think about having a star somewhere on Earth, that doesn't sound like a very sensible thing. Lots of energy, it's going to cause damage, okay? In RACE, we recognise that you're trying to create a star, and we're thinking about the bottle that you're going to put the star in.
Right.
Yeah?
Yep.
So that bottle is going to be damaged by the star, because the star that we're creating, this very, very hot plasma, is radiating stuff. That stuff is very energetic, so we've got lots of energetic particles that are flying off this plasma. Those particles are going to fly into the bottle, and the bottle is going to get damaged. So let's say if we were in there, we would just get vaporized, literally. I mean, because there's so much energy, which is what you want, but that energy would just destroy biological material. So we have to use robots that are made of metal. We have to use a bottle that is made of metal so that it actually can last.
I hear we're talking about 100 million degrees inside that bottle. But how is that even possible on Earth?
First off is, we're not really talking about temperature in the way that we sort of feel it in an oven, right? It's not hot like that. This is actually about kinetic energy, so it's about speed. We got these particles that are coming off, and they're moving really, really fast. Okay, so it's like billiard balls or things like this. Not quite. That analogy doesn't quite work. But billiard balls that have got lots of energy and they're moving really, really fast. When those hit things, like if you were hit by a bullet. These are really, really minute bullets that are moving. It would hurt, right? It would dissipate the energy into you and you'd fall apart. So what we're doing is we put it inside a magnetic cage. That's okay for the charged particles. We can keep the charged particles within a magnetic cage, within a magnetic bottle.
Charged particles such as?
An alpha nucleus, or an alpha particle, which is a helium nucleus.
Which is formed when you fuse the different types of hydrogen.
Yes. So let's back up. So the fusion reaction is where you combine two types of hydrogen, Those are deuterium atom and a tritium atom without their electrons, because that happens when you get into a plasma when it's very, very hot. When you combine those two things together, what happens is you create an alpha particle and a neutron. So that energy is carried away in the form of kinetic energy. So the alpha particle is moving, it's not stationary, and the neutron is moving really, really fast. So yeah, that's what we mean by 100 million Kelvin. It's
Speed of the particles.
Yeah, it's the energy which is within the stuff that is released when you do fusion.
Okay, so you're using a magnetic field to contain all that energy in a bottle.
Yep.
But not the neutrons, because they're neutral. They can escape the magnetic.
Exactly. So the neutrons are flying off in any direction. They're not charged, so you can't control where they go with a magnet. So they're going to go wherever they go, and that's a problem because they've got the energy. We want to rip the energy off them and create electricity.
So the magnetic field inside the tokamak contains the superheated plasma, and an internal vacuum creates an almost perfect insulating layer between the hot plasma and the sides of the chamber. But the high energy neutrons released during fusion can travel through both the magnetic field and the vacuum. I think in a lot of people's minds, you stick a plug into a fusion reactor. That isn't how you get the energy out. How do you actually get the energy out?
Okay, so the bottle that contains the plasma becomes hot. We then stick that hot thing in a load of water or helium or some other coolant. It heats up that coolant, and then we can make that coolant flow away to somewhere where we can actually take the energy out of the coolant. So there are these heat exchange cycles which move the energy away from the plasma to the turbine, which creates the electricity.
Most of us, when we read about fusion, don't think of it as radioactive. We think of fission as radioactive, but fusion as completely benign. In what way is it radioactive?
Well, the neutrons have so much energy that when they pile into the bottle, they change the materials in the bottle to become active.
And what do you mean by activated materials?
Materials that then radiate themselves.
Right.
So let's say you've got an aluminium atom, that's probably a bad example, but you know, an aluminium thing which is not active, if you hit it with enough energy, you can make it go to a state which then does become radioactive. And that sort of thing is happening with the steel and with other things that are in the bottle.
Which is why you need all these guys, these robots. People can no longer go inside it.
Yep. It's slightly worse than that, actually. We probably can't go near it. So at the moment in jet, we can't go inside jet, but we can get near the machine. But when you start to get to the powers that you require for a power plant, actually you won't go in the room that the reactor is sat in. So actually the robots have got to do a lot of work. So we'll have a facility which is basically maintained by robots with people further away, which brings me back to why race is called race. It's remote applications. The people are remote from the hazard. They're controlling the robots that are doing the work on the hazardous plant. And
one day, when it comes time to decommission the bottle you talked about, it'll be all robots, won't it?
Yep. So we're thinking about the whole life cycle, and that's very important as well.
Even though we've focused a bit on any possible radioactivity, overall, nuclear fusion is a lot safer than fission. For a start, there's no chance of a runaway reaction such as what happened at Chernobyl. And it's important to remember that even though the reactor itself will become radioactive, any resulting waste will be a tiny fraction of what is produced by traditional nuclear fission plants. And it's expected that materials from the tokamak will be able to be recycled within 100 years, whereas waste from nuclear fission can remain dangerously radioactive for thousands. Maddie Kearney is one of a number of mechanical engineers working at RACE. What's going on here?
So we're just doing some graduate training at the minute. So this is our AIM2 cell, which stands for Automated Inspection and Maintenance Test Unit.
So you've designed these robots for maintenance and testing?
So the robots are off-the-shelf robots. We've designed this cell to enable us to automatically maintain and inspect.
There are a multitude of robots in this huge hangar, from small robotic arms to monsters such as these, all focused on a different task that will be essential for running the fusion reactors of the future. Jobs such as repairs, refueling and replacing components, and eventually decommissioning. What have we got here? This seems a bit gruntier, for want of a
yeah, so
scientific
this is a much bigger standard robot that you can buy. Obviously it's much bigger, so it's much more expensive.
But this will be controlled by, at this stage, by a person remote controlling it.
So not with this, it's somebody writes a program and then they set commands which allow them to automatically run the software.
So this is kind of the same sort of robot that you'd see in a car factory.
Yeah, they're very similar robots. It's just different software. So again, it's software development that's going on here.
So even though these machines are very big and grunty, we're actually talking about what you're working on is not the hardware, it's the brainware, the software for these.
Yeah, so a lot of these, they're just off-the-shelf robots. So the research that we're doing is all about the software development.
But you're also developing engineers of the future over there.
Yeah, we have a lot of graduates. Every year we get a big intake of graduates, so we're doing some training, so just a bit of appreciation of how the robots work.
350 people a year are being trained to be the fusion engineers and technicians of the future. So one of those graduate students we saw this morning in 2040 may be the one who switches on STEP.
Yeah, exactly, yeah. That's the plan.
It's a good plan. The power plant will also create many jobs for people in the area, and the general response from locals has been positive. Andy, most people, when they think about big infrastructure projects like this new STEP fusion reactor, think not in my backyard. But you want it in your backyard, don't you?
Well, as a group, we've consulted friends, we've done a lot of outreach to people to find out, and on the whole, people are enthusiastic for it. When the coal mines closed and the coal-fired power stations closing, you're losing a lot of good, well-paid jobs. Also, there's a lot of support industry to it. Now, the industry has found other things to do, but we don't need more distribution centres and things. What we need is some technology that we can build off and that will give rise to other jobs and things and to education, and that's why it's a good project.
But how do you personally feel about this? Because looking at the colour of both of our hair, we may not be around when this thing finally gets going.
I have a grandchild, I have a grandson, looking forward to his time. If we can come up with a really green source of energy, then that's a huge benefit. And not just for this country, but for the whole world. So this is going to be a prototype fusion power station, but will it provide power to the grid?
Yeah, so the point of STEP, its absolute fundamental point, is to put electricity on the grid, to demonstrate that that's possible from a fusion power plant. So the idea is that we generate around 100 megawatts of electricity. That's our sort of aim, and then that builds to the commercial plants of the future.
How much is 100 megawatts in terms of houses powered, for example?
Yeah, basically it's a small village, I would say.
This is a personal question. I don't want the scientific or the political answer. Do you feel confident that in 2040 this place will be putting energy into the grid, even a small amount?
These projects of any scale are always tricky, but yeah, I mean, I look at the work that the team are doing day in, day out. It gets me excited every day. I love coming to work for that reason. So there'll be plenty of challenges along the way, but yeah, I have reason for confidence that we'll get there 2040.
So our view is that if we aren't ambitious, we will fail. You have to put a marker in the sand and have a go. We know it's probably the most difficult problem on the planet, but if you don't have a go, you'll fail.
You're literally reaching for the star on Earth.
Yeah, I mean, so if we can make fusion work on Earth, it's the power source that powers the whole of the universe. If we can make that work on Earth, then we have changed humanity's future.